For the last, well, I'd say the last few years, really,
Yeah.
the entire architecture of artificial intelligence has operated on this hidden assumption
Yes.
that we're all just tenants.
Yes.
We rent space on these massive server farms. We agree to terms of service
A
dictated
very
by,
small handful.
like,
Yeah.
exactly. And we just accept that if we want access to top-tier frontier AI, we have to play by their
Which
rules.
means using their infrastructure.
Right. And the prevailing narrative has always been that building one of these frontier models requires, just infinite
Oh,
capital.
yeah.
Tens of thousands of GPUs, an army of PhDs.
It's the billionaires club, basically.
Yeah, exactly.
Y-
But today, in this deep dive, we were looking at something that, well, it fundamentally dismantles that entire assumption.
It really does.
Yeah. We're looking at the Thomson 1.0 technical report. This was published by researchers from Thomson Reuters, Imperial College London, Datology AI, and Lambda. And the mission today is to figure out how they essentially laid out a blueprint to stop renting and, buy the building outright.
Yeah, the Thomson 1.0 report it is easily one of the most structurally disruptive papers we've seen this year.
Without a doubt.
It takes this concept of sovereign AI, which, it has been a theoretical talking point for a while.
Right, a buzzword.
Exactly. But this moves it into a fully realized, economically viable engineering framework.
Which is huge. Oh, sorry, go ahead.
No, you're right. I was just going to say, they didn't just theorize about democratization. They actually built, like a model factory.
Yeah.
And they did it with fewer than 36 engineers
Wow.
and a hard ceiling of 368 B200 GPUs.
Which is just, we'll get into the numbers later, but that is pocket change in the AI world.
It really is. They proved that having specialized, localized control over frontier-level intelligence is physically and financially possible today.
So before we get into the actual mathematical reality of running a 397 billion parameter model on a cluster that small,
Yeah,
I think we should define the problem they were trying to solve.
I agree.
Because the report frames the current AI landscape as this environment defined by a severe asymmetry.
Yes, a profound asymmetry on really three distinct levels.
Okay.
There's an information asymmetry, an economic asymmetry, and a power asymmetry.
Right.
So think about it. The developers who train these massive general models, they dictate the pre-training data.
So they decide what the model actually knows.
Exactly. They control the baseline knowledge and all the behavioral guardrails.
Mhm.
And then economically, they control the pricing. They set the API limit
Which can change at any time.
without worrying, yeah. And consequently, they hold ultimate power over the deployment of the technology. So the end user, and even a massive multinational corporation.
Right. Fortune 500 company.
Yeah. They are ultimately beholden to this totally opaque system. Their proprietary data is often, sent off premises.
To some cloud they don't own.
Right. And the model's underlying logic could just change overnight with an unannounced update.
Okay, let's unpack this because I love an analogy.
Sure.
Relying on big tech for AI is kind of like renting an apartment where the landlord they can change the locks whenever they want.
Yeah.
You can jack up the rent, and they can basically look through your windows whenever they feel like it.
That is exactly it.
So sovereign AI is about finally buying your own house.
Yes.
And the report breaks this down into 5 functional pillars, right? Because it isn't just about owning a server in a closet.
No.
It's about total control over the intelligence engine, keeping your private data entirely in-house, aligning the model to, say, your specific institution's internal ethics or standards.
The governance piece.
Right. Controlling the open source infrastructure, and ultimately operating at the raw cost of compute rather than paying, a massive markup to an API provider.
Right. And what's fascinating here is that the consolidation of those pillars, that's what creates a truly localized intelligence system.
Okay.
Because when an organization controls the data pipeline, the infrastructure stack, and the training mechanics, they basically decouple themselves from Silicon Valley.
They cut the cord.
Exactly. They're no longer sitting around waiting for a general purpose model to get marginally better at their specific domain.
Right.
They are driving that domain expertise themselves.
But wait, I have to push back here for a second.
Okay, go for it.
Because if we look at the actual methodology in the report, they didn't build this from scratch.
No, they didn't.
The Thomson team, they used existing open-weight models as their foundation.
Right, specifically the Quen 3.53997b.
Right, and the Quen 3.635b.
Yes.
So if you're building your entire architecture on top of a foundation, you didn't pick it out, and the initial weights were set by some other company, how is that actually sovereign?
That's a great question.
Because you're still relying on a baseline dictated by another developer, right?
Yeah, and that limitation is very real. And to be fair, the researchers are completely transparent about it.
Okay.
You do not have what they call foundational sovereignty over those initial petabytes of internet data.
The data that taught it basic English and facts.
Right. The stuff that establishes the base syntax and general knowledge.
Yeah.
But they're arguing for something else. They call it functional sovereignty.
Functional sovereignty, okay.
So while you didn't pour the concrete for the foundation, you achieve absolute control over the structure you build on top of it.
I see.
You get that functional sovereignty in the mid-training and the post-training phases.
By doing what?
By taking that open weight model and just entirely controlling the environment it runs in. You isolate your sensitive private data so it literally never leaves your physical perimeter or your private cloud.
Okay.
And you mathematically force the model to align with your custom directives.
So you're overriding the default behavior.
Yes. You sever that reliance on the original developer. So the model effectively becomes a closed loop governed entirely by you.
Okay, that distinction makes sense. So foundational sovereignty is basically a multi-billion-dollar problem.
Right. Let big tech pay for that.
Yeah, exactly. But functional sovereignty is an engineering problem.
Yes.
And to solve that engineering problem, they had to physically modify these massive open weight models without ruining them.
Which is incredibly hard.
Because we know that standard fine-tuning doesn't really work for injecting deep, complex knowledge into an LLM, does it?
No, it doesn't. Standard fine-tuning is effectively just surface-level behavioral modification.
By changing the tone of voice.
Exactly. It adjusts a very, very small percentage of the parameters.
Yeah.
So it's great if you want the model to answer in bullet points or sound more polite.
Right.
But it struggles to impart rigorous, deep domain knowledge. If you try to use basic fine-tuning to force a model to memorize and synthesize, say, complex international tax law.
Oh, boy.
Yeah, you trigger what's called catastrophic forgetting.
Because neural networks learn by adjusting weights, right?
Yes, through backpropagation.
Yeah, right. Backpropagation to minimize errors on the new data. So if you just flood the network with dense tax law, the gradients force all the weights to optimize only for tax law.
Exactly.
And in the process, they just overwrite the pathways that handle basic logic.
Or general reasoning.
Yeah.
The network literally cannibalizes its own general intelligence just to make room for the new specialization.
Oh, wow. So it becomes like a highly proficient tax analyst that suddenly struggles to write a coherent sentence.
Or parse a simple coding problem.
Exactly.
Yeah, it's wild.
So to bypass this, the Thomson team utilized something called continual learning.
Now, continual learning, that gets referenced a lot in these papers.
It does, but people rarely unpack it.
Right. So how did they actually execute this without triggering that catastrophic forgetting we just talked about? Because they didn't rely on distillation, right?
No, they avoided distillation.
Which is usually the shortcut. Right, where a smaller model just mimics the outputs of a larger teacher model.
Right.
The problem is distillation implicitly accepts a ceiling. The student model can approach the teacher, but it rarely exceeds it.
It can't be smarter than its teacher.
Exactly. Continual learning, by contrast, involves making full-weight updates.
Full weight, so the whole network.
Yes. They are unfreezing and altering the core parameters across the entire massive network.
That sounds risky.
It is. To do it without causing neural collapse, they have to maintain this incredibly precise mathematical tension.
Between what?
Between plasticity, which is the model's capacity to absorb the new complex knowledge, and stability.
Meaning not forgetting the old stuff.
Right, preserving its foundational capabilities.
Here's where it gets really interesting to me. It's like learning a complex new language, right?
I like that analogy.
Narrow fine-tuning is like cramming for a vocab test and then just forgetting it the next day.
Yeah.
But continual learning is mastering the new language while ensuring you don't magically forget how to speak your native tongue in the process.
Exactly.
But how do you enforce that stability technically? Are they freezing specific weights, or is it like a data routing thing?
It's actually a really sophisticated orchestration of the learning rate, targeted weight consolidation, and highly engineered data replay buffers.
Okay, break that down for me.
So rather than just blasting the model with domain-specific data, they interleave a meticulously calculated percentage of general knowledge data during the mid-training phase.
So they reminded of the old stuff while teaching it the new stuff.
Right. They're constantly forcing the model to revalidate its general reasoning pathways while
Wow.
simultaneously etching the new specialized pathways.
Wow.
And the algorithms are mathematically penalized if they deviate too far from the optimal weights that govern general syntax and logic.
So it has to find new room.
Exactly. It forces the network to find new dimensional space for the specialized knowledge rather than just overriding the old
And
space.
the report visualizes this outcome as a pie-shaped pattern.
Yes, like the Greek letter pi.
Right. So if you picture that, the broad horizontal bar across the top represents the model's general intelligence.
It's baseline reasoning, language comprehension, stuff like that.
Right. And then the two vertical legs coming down, those represent the incredibly deep, localized mastery in distinct fields.
Like legal analysis and tax structuring.
Right.
And what's amazing is the continual learning architecture didn't just maintain that horizontal bar of general knowledge, it actually elevated it.
Wait, really? It got better at general stuff?
Yes. By deepening the model's understanding of complex, highly structured domains like law and tax, the underlying reasoning capabilities improved across the board.
Oh, I see.
The model learned to synthesize complex arguments better in the legal data, which then translated back into its general capabilities.
That compounding effect is incredible.
Yeah, it allowed this 36-person team to bridge roughly 7 months of industry-wide capability gains.
That's a lifetime in AI.
It really is. They took architectures from late 2025 and pushed their performance straight into the frontier landscape of mid-2026.
Okay, so continual learning is the engine that allows the model to expand without collapsing.
Right.
But an engine is entirely dependent on the fuel you put into it.
Absolutely.
And the Thomson 1.0 report really highlights a fundamental shift from a model-centric approach to a data-centric approach.
Yes, this is a huge takeaway.
They basically treated the neural architecture as a solved variable.
Right. They didn't mess with the math of the network too much.
No, they poured almost all of their engineering resources into the data pipeline itself.
Because the historical approach has always prioritized architectural tweaks. Scaling parameters, modifying attention mechanisms, tweaking the algorithms.
Throwing more math at it.
Right. But the Thomson researchers recognized that at a certain scale, the architecture is commoditized.
Yeah.
The true differentiator, and really the only way to achieve that pie-shaped capability curve without massive compute, is hyper-refined data curation.
They engineered the diet of this model with just an unprecedented level of granularity.
You really did.
Let's look at the mid-training phase. Because they weren't just taking raw legal repositories and just dumping them into the model.
No, the data preparation was aggressive.
The report details extensive rephrasing of source material. They used aggressive filtering to remove low-density information.
Lots of strict deduplication.
Right. And even artificially enhancing the data to ensure the model was extracting the exact conceptual relationships it would need later on.
And that mid-training preparation is crucial because it creates a compounding efficiency.
Right.
By increasing the density and the quality of the mid-training corpus, they dramatically reduce the computational burden required during the supervised fine-tuning and post-training phases.
Which saves money.
Exactly. And when they reached that post-training phase, they employed Bayesian optimization to manage their data mixtures.
Okay, Bayesian optimization. That is a concept that often gets glossed over as just a testing algorithm.
Oh, totally. People just brush past it.
Yeah. But it is fundamentally a probabilistic approach to navigating uncertainty.
Yes.
When you are mixing data, like deciding whether a training batch should be, say, 30% legal reasoning, 15% conversational dialogue, and 55% general logic.
The search space of all those possible combinations is virtually infinite.
Right. Running a full evaluation on every single permutation would consume more compute than the entire training run itself.
Easily.
So Bayesian optimization tackles this by building a surrogate mathematical model of the performance landscape.
Right. It starts with an initial assumption.
A prior.
Yes, a prior about which data mixtures might work best. And after running a small targeted test, it updates that assumption based on the actual performance.
The posterior.
Exactly.
It functions, well, I like to think of it like a radar system trying to track a highly evasive target.
Oh, that's a good way to put it.
It doesn't scan every square inch of the sky with equal intensity. That would take too long. Right. It sends out a ping, registers a faint signal, and then uses that
Triangulating the optimal position.
Exactly, while just ignoring all the empty airspace. It balances exploration, testing entirely new data ratios to see if there's a hidden performance spike with exploitation.
Drilling down into the specific ratios that are already showing promise.
Yes.
So the Bayesian algorithm systematically narrows in on the absolute optimal data recipe required to maximize the model's performance across all the benchmarks simultaneously.
Amazing.
And it entirely automates a process that usually requires massive amounts of trial, error, and wasted GPU hours.
And the automated aspects of this pipeline are deeply impressive.
Yeah.
But the report also leans heavily into human intervention for the high-stakes domains.
It has to, really.
Right. To curate the data for complex tax structuring or legal analysis, they actually utilized human subject matter experts.
Yeah.
Because they recognize that an algorithm can optimize a mixture all day, but it cannot intrinsically gauge the nuanced accuracy of a complex legal argument.
No, it can't. To build an intelligence engine for professionals, the baseline truth has to be established by professionals.
By real lawyers and accountants.
Exactly. But the bottleneck in that approach has always been scale. You can't hire enough human experts to curate billions of tokens of data.
Not without going bankrupt.
Right. So the Thomson team navigated this by using LLMs as judges to scale the curation process.
Essentially, having AI grade the homework of the AI being trained. But logically, using an open-weight LLM to judge the training data for a new model, doesn't that introduce a capability ceiling?
How do you mean?
Well, if the AI acting as the judge only possesses the reasoning capacity of a mid-tier model, it can't effectively identify or curate data that requires frontier-level reasoning.
Right. If your teacher is a B+ student, how do you ever get an A?
Exactly. How do you ever surpass the capability of the system you are using to evaluate your own data?
The solution lies in the self-improving loop generated by the continual learning pipeline. So the researchers initially used the highest-performing open-weight models available as their judges.
Right.
But because of the compounding efficiency of their mid-training phase and the structural advantages of continual learning that we talked about, the Thomson 1.0 models eventually eclipsed the reasoning capabilities of the very models used to judge them.
Oh, wow. So the model bootstrapped its way past its own curators.
It did. And the implications of that are profound for sovereign AI.
Because you don't need the outside models anymore.
Exactly. For subsequent iterations, like a hypothetical Thomson 2.0 or 3.0, the organization is no longer reliant on external open-weight models to act as judges.
They can just use their own stuff.
Right. They deploy their own superior proprietary models to curate the data for the next generation.
That's incredible.
They have successfully ignited a localized, self-sustaining loop of intelligence generation that requires zero external dependency.
Which brings us to the actual operational reality of what this self-sustaining loop produced.
The receipts.
The receipts, yes. If we look at the constraints this team operated under, the numbers run completely counter to the industry consensus.
It's almost hard to believe.
We are talking about a maximum of 368 B200 GPUs.
Right.
Meanwhile, the major AI labs are currently linking clusters of 100,000 GPUs to train their frontier models.
It's David and Goliath, truly. And beyond the compute constraints, the human capital was incredibly lean.
Yeah.
Fewer than 36 engineers and scientists.
Which is nothing.
Nothing. And the total development timeline, from the initiation of the project to the finalized weights of both the small and large models, was just 3 months.
3 months?
They essentially collapsed the entire development cycle.
And the financial breakdown is really where this concept of the model factory crystallizes.
Yeah, let's talk about the money.
The report transparently lists the total research and development cost at roughly $40 million.
Which sounds like a lot.
Right, but that figure represents the capital expenditure required to build the infrastructure.
The factory itself.
Yes. Staff salaries, human expert compensation, vendor partnerships, the creation of the reusable pipelines.
The $40 million builds the factory and calibrates the machinery.
Right.
But the actual marginal cost to produce the model, the raw compute expenditure for the final training run of the Thomson 1.0 large model, it was under $450,000.
I mean, in the context of frontier AI development, $450,000 at a rounding error.
It is a fraction of what is typically spent on a single training run for models in this capability tier.
It's literally David beating Goliath, but David built a better slingshot out of open source parts.
I love that. And the benchmarks prove that this wasn't just, a budget-friendly compromise.
Not at all.
The performance metrics are the ultimate validation of this methodology.
Right.
The Thomson 1.0 large model didn't just remain competitive with the open source community.
No, it surpassed them.
It surpassed heavily funded proprietary flagship models that were released months later.
Give us the list, because this is wild.
It outperformed Claude Sonnet 5 and GLM 5.2 from June 2026.
Wow.
It beat GPT 5.5 and DeepSeek V4 Pro from April 2026.
Which were industry darlings.
Oh, yeah, and it beat Gemini 3.1 Pro from February.
And it did so across a massive spectrum of evaluations. It wasn't just a one-trick pony.
No.
It dominated in agentic tasks, demonstrating the ability to plan, use tools, and execute multi-step reasoning autonomously.
Yes.
It set new benchmarks in legal and tax analysis, multilingual processing, safety evaluations.
All of it.
When a model trained on 368 GPUs for $450,000 in marginal compute outreasons proprietary models trained on tens of thousands of GPUs, it just forces a complete reevaluation of how artificial intelligence scales.
It absolutely does. It demonstrates that the relationship between brute force compute and model comparability is not linear.
If not just more GPUs equals more smarts.
Exactly. There is an asymmetric efficiency available to organizations that prioritize data-centric pipelines and continual learning over sheer scale.
Quality over quantity.
Yes. The Thomson report is proof that if your data architecture is flawless and your parameters are updated with surgical precision, you can achieve frontier intelligence at a localized scale.
And the implications of this blueprint extend so far beyond the specific legal and tax models that this team built.
Right. This is just the proof of concept.
Exactly. This report fundamentally democratizes the mechanics of frontier AI. It proves to enterprise leaders, developers, institutions, everyone really, that the economic barrier to entry has just evaporated.
It's gone.
You do not need a billion-dollar data center to build a world-class intelligence system tailored specifically to your proprietary data.
No.
You need rigorous data curation, an understanding of Bayesian optimization for your mixtures, and a continual learning pipeline that prevents catastrophic forgetting.
The technical execution here validates the entire premise of sovereign AI.
Yeah.
It shifts the power dynamic entirely away from centralized tech conglomerates and distributes it outward.
Right to the edges.
Yeah. We are moving from an era where intelligence is a massive monolithic utility that we rent into an era where intelligence is highly specialized, hyper-localized infrastructure that we own.
If a small, dedicated team can achieve this level of performance in 3 months using a few hundred GPUs, the natural question for the listeners, how does this scale horizontally across different sectors?
Well, the proliferation of this model factory concept is the most compelling aspect of the report, really.
Yeah.
Consider a near-future scenario where every major hospital system trains a sovereign medical model, right?
Oh, wow.
They're continually updating it on their proprietary patient outcomes without ever sending a byte of sensitive data to a public cloud.
Complete privacy.
Exactly. Or consider municipal governments deploying specialized civic management models.
Right.
Or aerospace firms running highly restricted engineering models on air-gapped internal servers.
If they can finally afford to.
Yes. When the cost of frontier intelligence drops to the marginal cost of a few weeks of GPU time, the center of gravity in the technology sector fundamentally shifts.
It changes everything.
It does. Silicon Valley is no longer the sole landlord of artificial intelligence. The architecture has been open-sourced, and the tools to build completely independent, sovereign intelligence systems are now available to anyone willing to execute the blueprint.